Layout design for augmented reality applications. Augmented reality applications can be as simple as virtual screens floating in front of the user, or require special markers in order to embed content in the scene. An application which factors in the environment and adds virtual objects seamlessly into the scene provides a more immersive experience. The challenge we tackle in this paper is, how do you design an immersive AR application to work anywhere? Consider a racing game, for example. A completely virtual game can be designed completely in advance. However, in an augmented reality racing game, we want the track to be exciting, winding between obstacles, climbing tables and chairs. Therefore, the track layout must be created at runtime. We create a dynamic racetrack targeted to a room in the following manner. The developer specifies the required length of the track. Then, we analyze the room's geometry to locate horizontal surfaces we can use and avoid collisions with existing objects. We place key points whose number is proportional to the length of the track in the room on the detected horizontal surfaces. Each key point is within a set distance range from the next key point and has line of sight to it. We render the racetrack as a spline passing between the key points. We demonstrate various tracks of different lengths targeted to this office and other rooms. All the tracks are generated automatically using the same rules in different environments. To illustrate our approach, consider a chess puzzle where the chess board is our room and the chess pieces are the application components. Let's say we want to place a black pawn, a black knight, and a white queen, such that the knight threatens the queen and the pawn does not. We term these rules self-consistency constraints as they describe the relationship between application components. If the board is otherwise empty, there are many solutions which are relatively easy to find. However, if the board might contain obstacles which are not known beforehand, we can only find a solution once they are revealed. We add rules addressing the unknown environment, which we term scene consistency constraints. In this example, the chess pieces must not collide with existing objects on the board. Given the complete set of rules, we can now attempt to solve the chess puzzle anywhere. Now consider a room. Let's say our application has two objects in it, these guys. Their size is fixed, but we would like to position them in the room and set their facing. Let's add a few rules, namely, they must stand on the floor, should be around 2 feet apart, and look at each other, all within the camera's field of view. Here's the solution our algorithm found. In the next scenario, we have 9 of them, and we want 8 of them to stand in a circle facing the 9th. We do not constrain the radius, only spread them evenly around the center guy, like this. If the room was of a different layout, for example, contained a dining table with chairs, we would find a different solution, although the rules have not changed. Finally, let's say someone stepped into the scene, breaking one of the rules, in this case stepping on one of the objects. We resolve while adding a constraint that the new solution be as similar as possible to the previous one. Our move-making algorithm utilizes a novel approach we term locally satisfiable proposals. The key idea is that for many types of rules, satisfiable assignments can be found efficiently. Take this scenario for example. Given a position for the center object, the other objects should be placed in a circle of some radius. The position of a second object determines the radius and significantly reduces the sampling space for the rest of the objects. For details, please see the paper. Following are additional examples of applications enabled by our system. Angry Cannon is a game in which a user aims a really angry cannon at brick castles and bomb pillars around a room, attempting to knock them down. A physics engine is used to compute the cannonball trajectory and simulate the collapsing castles. The constraints are such that the brick castles and bombs are close to each other, while the cannon is a minimum distance away from them and facing in their direction. The media library application displays the user's movie collection, organized by theme, on panels with revolving content. 2 virtual video screens on the walls show clips from suggested movies. The constraints are such that all screens are within the user's field of view, the panels stand on horizontal surfaces, and the video screens hang from the wall as big as possible and are aligned either horizontally or vertically. In conclusion, we developed a framework for rule-based AR application layout, solved using a novel move-making algorithm. Our algorithm was designed with low-powered devices in mind, reducing the number of layout evaluations required. Thanks for watching.